Now we're going to look at things that are moving vertically and moving vertically under gravity. Now, we all know that if we drop something or we throw something into the air, it will start to move towards the ground. And this is because the gravitational field around the Earth pulls everything to the center or pulls everything down towards the floor. Now, this is an acceleration of that object, and we'll refer to it as the acceleration due to gravity. Now, this is a fixed value while you're on the planet Earth. Sometimes people's intuition leads them to think that the rate at which your speed changes as you fall through the air is going to be different depending on the mass, depending on the weight of the object. Now, we know actually every object experiences the exact same acceleration. The reason you may well think that something lighter or something of a different shape will fall at a different speed will be if it's experiencing air resistance. Now, in all of the work that we do, in the models that we work with, we regularly model things as particles, meaning that air resistance is not going to play a factor. So when air resistance is negligible, objects all have the same acceleration towards the ground. And we have a fixed value for that, 9.8. And we have some notation that we use in maths, which is the letter G. So anytime you have an object moving vertically, freely, so it doesn't have any additional forces, it's not connected to anything else, it will experience acceleration or deceleration due to gravity, which has a value of 9.8. Other subjects use different values very specifically in the maths course, in your maths studies, in your maths exams. You must use 9.8. Trying to use a different value, even if it seems more accurate, will actually get you penalized. Marks will be taken off for using a different value that you might use in a different subject. So 9.8 is what we'll focus on. You may be interested to know that this is very specific to Earth and Earth's gravitational field. Other planets, other celestial bodies, if you're out in space, if you're on the space station, you will not have the same value of G. You will not have the same acceleration due to gravity. On the moon, that acceleration is about 1/6 of what it is on Earth. So things on the moon will accelerate at a much lower rate. Okay, just to make sure you've got some context around how things will be different when we're moving vertically, the acceleration that we might have been finding before, we are now expected to know and to use. It's going to be 9.8 or negative 9.8, and I'll explain how to choose which of the two you'll use. So be on the lookout for this phrase or for the context letting you know that an object is moving freely under gravity. If that's the case, there's an expectation that you can use 9.8 or negative 9.8, and I'll explain further how to choose between the two, but you know that you're using acceleration of a magnitude 9.8 in your modeling. Okay, so just before we get into the examples, just wanted to talk about displacement. Now, displacement is a vector measure, and it's a measure from the point we're referring to back to the original point, back to the starting point, back to where t equals 0, back to where we defined our initial speed, back to the beginning of the journey segment. Now, sometimes people go wrong with these vector measurements, both velocity and displacement. So I just wanted to quickly run through that before we get to some examples. So an object may be moving to the right, that's the positive direction, but if it has negative velocity, it may well change directions. So a displacement of 10 is going to happen here, but it can happen twice, once on the way to the right and once after the change of direction when it's moving to the left. So we may have two incidences where we have a displacement of 10. So 2 times where that can happen, and we have formulas that help us to calculate those 2 times. The object may continue moving, and its displacement eventually will become 0 when it gets back to the starting point. And we know this because displacement is measured from our start point to the point we're interested in. Well, if they're both the same place, displacement must be 0. Now, if it starts to move towards the left, since our positive direction was right, everything on the left of our start point is going to be a negative displacement. We need to be really careful. Do values match the positive direction we've chosen? If we are to the right of the start point, the displacement is positive. If we're to the left of the start point, the displacement is negative. If we're moving in the same direction as our positive arrow, velocity is positive. If we're moving in the opposite direction, velocity is negative. Our initial direction arrow is quite important to set up our variables correctly. Well, this is true horizontally and it's true vertically. An object that is thrown into the air eventually will have a change of direction and start to come down. It will also have multiple times where the displacement is a specific value. If the object gets back in line with the point of projection, displacement will be 0. And if the object goes below the point of projection, then the displacement will be negative. The direction arrow, once again, informs us quite specifically what parity or sign we should choose to go with our variables. Now, in this first example, we're told that Harry throws a stone vertically downwards from a cliff top into the water. The stone has a velocity of 4.5 meters per second when Harry releases it and takes 5 seconds to reach the water. Can we calculate the height of the cliff? Okay, so as usual, we'll get a column of our Suvat variables, but we'll also get a diagram to show exactly what's happening. Now I'm going to draw the cliff top the same as I would any time that the object is thrown from a height. I'm just going to draw this little stack, this little platform, and I'm going to use this to model my cliff top. Now the stone that Harry throws is going to start here and it's going to move downwards towards the water. Since its initial direction was down, I'm choosing down as the positive direction. Okay, the cliff or the platform, I'm going to call its height h. To find h, I really want to find the displacement. So that's what we're looking for this time round. The initial velocity, we're told, is 4.5. Final velocity we don't know, but we don't need. The acceleration due to gravity is positive 9.8. Now, gravity always acts down towards the ground, which matches our positive direction, so I'm making that acceleration 9.8. The time that it takes is 5 seconds. We need a formula that uses S, U, A, and T. So that is our popular S equals UT plus half AT squared. We'll quote the formula, we'll substitute the values in. There's no rearranging, we just need to evaluate the right-hand side, 145 meters. That is the height of the platform. Okay, so straightforward one to get started. Next, and the situation you will more popularly come across, we're going to throw this object up into the air. Here we're told that Carl makes a bet with a friend that he can hit a ball more than 50 meters into the air with a cricket bat. He strikes the ball with an initial velocity of 22 meters per second, directly upwards from 1 meter above the ground. Did he win the bet? Let's set up the situation. Ready to collect our Suvat variables, and here's our diagram. Because the object started off of the ground, I'm going to draw the little platform, which I'll give a height of 1 meter. The ball is going to go up. Its velocity is going to be reducing all of the time. It will eventually have a velocity of 0, and then a negative velocity, and start coming down. Positive direction is up, because that's the initial direction the object started moving. Okay, let's go ahead and collect our Suvat variables. We're interested in when it gets to its greatest height. And as I said before, the change of direction occurs when velocity equals 0. This maximum height will have the velocity equal to 0. If the maximum height is more than 50, Carl will win his bet. If not, he loses the bet. Let's set up and collect our Suvat variables. The displacement is unknown. We're looking for that. Initial velocity of 22, Final velocity, the important bit here, is 0, and our acceleration is going to be negative 9.8. It's negative because gravity is acting down towards the ground, which is against our positive direction, which is in our negative direction. So acceleration due to gravity is going to be negative. We don't know the time, but we're not actually looking for it. We want a formula that uses S, U, V, and A, and here it is. V squared equals U squared plus 2AS. We'll substitute into the formula, and then we'll rearrange to find S. Okay, we don't really need to calculate each of these individuals, just going to get a fraction expression that we can put into the calculator at once. Negative 22 squared over 2 times negative 9.8. That's our displacement. When we evaluate, we get 24.7 meters. Okay, so Carl has hit the ball and he's given it a displacement of 24.7 meters plus the initial 1 meter above the ground. Well, this cricket ball gets to a grand total of 25.7 meters above the ground. That's nowhere near the 50 meters he was bragging about. He doesn't win the bet. He actually loses the bet and he has to pay up. So, because we knew we wanted the greatest height possible, we set velocity equal to 0 and we use that in our Suvat equation. Okay, one more for you. Here we're told that Rebecca is playing volleyball, hits the ball over the net, winning a point. She strikes the ball from a height of 1.5 meters with a velocity of 10 meters per second. How long does it take the ball to hit the ground? Okay, the diagram, like I say, whenever it's hit from a height, I'm always going to draw just this little platform. The ball starts from 1.5 meters, it travels upwards, it changes direction when velocity equals 0, and it starts to head back towards the ground. All right, which Suvat variables do we know? The displacement, well, it's below the starting point. The positive direction was up. The ball ends up below the starting point. The ball has negative displacement when it hits the ground. Displacement is going to be negative 1.5. Initial velocity we were given as 10. Final velocity we don't know and we don't need. Acceleration due to gravity is negative 9.8. Our initial direction was up. Acceleration due to gravity always acts down towards the ground. That is our negative direction. It's a negative value. Now that we have all of those correct, we're going to substitute into the appropriate formula. We want a formula that uses S, U, A, and T. So we have S equals UT plus half AT squared. So let's substitute our values in. We want to usually rearrange and make a variable the subject. But since we have T and T squared, this is a quadratic. We'll just get it into the general quadratic form, and then we'll go ahead and solve. You can use any technique you like to solve. You can complete the square. You can use the quadratic formula. You could factorize if the numbers were nice enough, or you can use the quadratic equation solver on your calculator. We get two answers. T equals negative 0.14 or T equals 2.18. Once again, one of these doesn't make sense in context. We're saying that the ball would have been on the ground 0.14 seconds before Rebecca hit it if it was following the model in the way that we've described. This doesn't make sense in the real world or in our scenario, so we eliminate that, and the only T we're interested in is T equals 2.18. So there we go. It takes 2.18 seconds for the ball to hit the ground after Rebecca launches it over the net.